Hello, and welcome to this lesson on the extraction of highly reactive metals using electrolysis. In today's lesson, we will firstly understand why electrolysis is used to extract highly reactive metals. We will then understand the specific process used for the extraction of aluminium. So far, you've become familiar with the basics of electrolysis, including how it works with both molten and aqueous ionic substances. You've learned that electrolysis involves passing an electric current through a substance to cause a chemical change. You are also familiar with the need for different methods of extracting metals based on their reactivity. Today, we will explore one of those techniques which we briefly touched on, electrolysis. Let's dive into the main technique of using electrolysis to extract highly reactive metals, focusing specifically on the extraction of aluminium from its ore, bauxite. Firstly, let's recap why electrolysis is used. Metals that are higher up in the reactivity series than carbon cannot be extracted by reduction with carbon. For example, aluminium, which is more reactive than carbon, requires a different method for its extraction because using carbon would not effectively reduce it. Electrolysis, which uses electrical energy to bring about a chemical change, is ideal for extracting these reactive metals from their ores. Now, let's look at the specific process of extracting aluminium. The first step in extracting aluminium is obtaining pure aluminium oxide from its chief ore, bauxite. Bauxite contains aluminium oxide, along with impurities like iron oxides and silica. The purification process involves treating the bauxite with sodium hydroxide, which dissolves the aluminium oxide, separating it from the impurities. The resulting pure aluminium oxide is then precipitated and dried. However, aluminium oxide has a very high melting point, around 2000 degrees C, which would require a large amount of expensive energy to reach. To make the extraction process more economical, the purified aluminium oxide is dissolved in molten cryolite. For your interest, that is sodium aluminium fluoride. This mixture lowers the melting point to about 950 degrees C, reducing energy costs. The electrolysis of aluminium occurs in a specially designed electrolytic cell. The cell is a steel container lined with graphite, which acts as the cathode, negative electrode. Suspended in the molten cryolite aluminium oxide mixture are large graphite blocks that act as anodes, positive electrodes. Direct current power is supplied to the cathode and anodes. When direct current is passed through the molten mixture, electrolysis takes place. At the cathode, aluminium ions from the aluminium oxide gain 3 electrons and are reduced, producing liquid aluminium. This is represented by the equation Al3 plus molten plus 3E minus, which becomes Al, liquid. As liquid aluminium metal is formed, it collects at the bottom of the cell due to its density. At the anode, oxygen ions in the molten mixture lose electrons and are oxidized, producing oxygen gas. This is represented by the equation 2O2 minus molten becomes O2 gaseous plus 4E minus. Additionally, the oxygen gas reacts with the carbon in the graphite anodes to produce carbon dioxide. This is written as C, solid, plus O2, gaseous, which becomes CO2, gaseous. This reaction gradually consumes the anodes, requiring regular replacement. The liquid aluminium produced at the cathode is denser than the cryolite aluminium oxide mixture. It settles at the bottom of the electrolytic cell and is periodically siphoned off. The collected aluminium is then cooled and solidified. Further purification processes can be applied if necessary to obtain aluminium suitable for industrial applications. To summarize, the process involves dissolving aluminium oxide in molten cryolite, setting up an electrolytic cell with graphite cathodes and carbon anodes, and passing a direct current to reduce aluminium ions to liquid aluminium and oxidize oxygen ions to oxygen gas. The liquid aluminium is then collected, fulfilling the essential extraction process. In today's lesson, we covered that aluminium is extracted by first purifying aluminium oxide from bauxite through a process involving sodium hydroxide, which dissolves the aluminium oxide, separating it from impurities. The purified aluminium oxide is then dissolved in molten cryolite to lower its melting point, making electrolysis more energy efficient. We then took a close look at the electrolytic cell in which direct current is used to reduce aluminium ions at the graphite-lined cathode, producing liquid aluminium, while oxygen ions are oxidized at the graphite anode, generating oxygen gas. This oxygen reacts with the carbon in the anodes, forming carbon dioxide, which gradually consumes the anodes, requiring their regular replacement. The liquid aluminium, being denser than the cryolite aluminium oxide mixture, settles at the bottom of the cell and is periodically siphoned off and solidified for industrial use.